Yo, what's up guys? So today I'm going to be talking about my output function and my exit function. So I'm going to show you guys the code behind them, how I made it, and then I'll give you guys a demo at the end. But before I show you guys the code for the output function, we need to talk about what we need it to do. First thing we wanted to do is we wanted to identify the specified register. So if I put an R0, I wanted to open the memory address in RAM for R0. If it's, R1, I want to open the correlating register. If it's R7, I want to open the correlating register. So we need to figure out a way to get the program to translate R0 into a memory address that I can open and access. Then I want to create the hexadecimal digits. It's actually easier than it sounds. An 8-bit binary number can be broken up into 2 hexadecimal digits, and you just take the top 4 bits and the bottom 4 bits. So it's really simple. And I'll show you how I do that when we look at the code. Then I wanted to output the 2 digits right below the line where I inputted it, and then go to the next line so that when the program loops back around, it starts below the number. Now let me show you how I did that. So one thing before we start, I wrote this in my own assembly language. You do not need to know assembly to understand this. I made sure to label everything, and I'll kind of explain everything in English. So don't get overwhelmed by all this code. I'll try my best to just explain it normally. But let's get started. So this chunk right here, I labeled up here, it gets the value you want to output. Now the most important part of this chunk is this call9, which is basically just a function. A function compresses a bunch of lines into a single line that you can call repeatedly. So this call9, it's several lines, and I can call it as many times as I want. Now this call9 basically opens RAM to the specific memory address of that register. Now what this does is this is just taking R3, which is the R, and then it's taking R4, which is the, in this case, 0, and it's moving them to temporary, and R2, which are basically just kind of blank spaces that I can use to hold values. They're basically the inputs of my call9 function. Then I grab the value stored in that register and move it to R0. So not the R0 that I input, but the actual general purpose register R0 in my computer. Now that's my first goal checked off the list. It can identify which register I'm inputting and open it and grab the value from it. Then the next goal on my list is to make the hexadecimal digits, and this is what these lines do. So this chunk here makes the first hexadecimal digit, which is the highest one. It takes the 8-bit number, the 8-bit binary number, and shifts it down 4 bits. It takes the top 4 bits and basically puts them at the bottom 4 bits. Then I run this call27, which takes any 4-bit binary number, 0 through 15, and turns it into a hexadecimal digit. And then it saves it into R1. Now getting the second hexadecimal digit is much easier. It ANDs the 8-bit number with 15, which is 4 ones. And really what that does is it deletes the top 4 numbers, the top 4 bits, gets rid of them, turns them to 0, and saves the bottom 4 bits. And in that way I can run this call27, and that just gets the bottom 4 bits and turns it to a hexadecimal number. And then I save it to R2. Now that is goal 2 checked off the list, which is make my hexadecimal digits. Now for the part to output them. So then I run this call35, which grabs the current screen position. The screen position is really what spot in the screen the cursor is on, so where it's typing, really. And I store it in memory address 10 in my RAM. So then this call35 just takes that value and puts it into the computer. Not only does it grab the screen position from RAM, but it also checks if it's greater than 64. And so the screen has positions 0 through 63 because it's an 8x8 screen, 64 positions. And so it checks, when it grabs that position, it checks if it's greater than or equal to 64, and that would mean that the cursor is off the screen. And if it's off the screen, it runs a function called call23, and it clears the screen and then sets the current position to 0. And that's really important later. But really all this does is it checks if the output digits are going to be off the screen. If it is, it clears the screen. If not, it just grabs the current position. Then outputting the first digit, pretty simple, just output R1, which is the first digit I saved, and then output the current screen position. And then this moves it to the right one. So that's getting ready for the second digit, which is just R2. Same thing again, outputs the current screen position. And then what this does is it goes to the next line because I'm thinking about my next iteration, the next function I want to run. So what I do is I add 8, and it basically skips it to the next line, the line below the outputted hexadecimal digits. So in that way, I'll just start right under the hexadecimal digits. And then this load IAR 42 jumps back to the beginning. So this is all the exit function is. It's very, very simple. I didn't even bother making an extra file for it. And all it does is it runs this call 23, which I said earlier, clears the screen, and then it loads instruction address register 0, which basically just halts the program. So after that, we have checked our third and final thing off of our goals for our output function. So let's do a quick demo. So I could do something really fancy, I could use dozens of lines of code, but that's just distracting us from the fact that this is a very, very, very simple function. It's literally just seeing a value inside of the computer. So I'm just going to do a very simple demo for you guys. I'm going to load to register R2 the value C5, and then I'm going to output R2 so we can see the C5, and then I'm just going to exit the program. So next week, I'm going to make a video on the add and subtract function, so stay tuned for that. Peace.